probably something that you might guess when you know a bit of the work of Jacques, but is not obvious, is that by training, actually, he's not an astronomer, but a mathematician originally. And speaking of mathematicians, of course, we are also at IAP in an area where we have lots of cosmology, exoplanet, etc. So you might think how I could be able to speak about Euclid during as an introduction to Jacques, and I'm going to do that. So Euclid, before being a space mission, is actually a Greek mathematician. So he gave a mathematical description of what we call the Platonic solid. So you know there are polyhedra, there are 5 of them, whether they have 4, 6, 8, 12, or 20 faces. And this thing in the old days was really in the quest for perfection. So in 16th century, Kepler was trying to associate these different polyhedra with actually the planets, not the Earth, but the other planets that were known at the time. Since you have perfection in the skies, you must have a mathematical link between this perfect Platonic solid and the planets. So yeah, 6 is nice and elegant, it's good. And then complexity increase when you start to have new tools to discover and study our world. And for example, Laplace and Lagrange thought that we had quasi-periodic solutions for the planet of our solar system. Anyway, quasi-periodic, yeah, it's still fine, nice and easy, nice, elegant. Everything was okay until the mess arrived in 1989, thanks to Jacques, where Jacques showed us that actually the orbit of the planets, they are not as nice and easy as you might think, and that actually they are chaotic. So he showed us that the trajectory of the planets are diverging in an exponential way. And just as a wet finger estimate, well, maybe at 10 million years, you will know where the planets are, but at 100 million years, you have no clue what will happen. And you may have a chance to have collisions of planets. And there is one recent aspect of the work of Jacques that is actually very nice, and is what we're going to hear about today, is actually the link between paleoclimate, the eccentricity, and the obliquity of planets. How can you try to get these kind of constraints? That's something that is really new and really fun. I will finish by adding that Jacques has been mentoring a large number of students and postdocs. Lots of them are still in our community today, including my former Padawan Federico Mogavero, who is now based in Italy. So in an aura of cosmology, we are going back to basics. We are going back to Earth Moon. Thank you, Jacques.
Thank you. Thank you for the nice introduction. And yes, I will speak of a very close subject with respect to what you are accustomed here, because I will speak of the Earth and the Moon. Usually people think that if it's close, and I will speak of relatively classical physics, but so you think that if it's close and if it is classical physics, everything is known. In fact, it is not true, and there are some fundamental issues that are not known, and I found this outrageous. So this is why I try to work on this. And it is not, the problem is when you decide to work on a subject, on an object, and not take a toy model that you know how to solve or how to tackle, things become much more complicated because you need to take the real thing into account. And in this case, it was tidal effect. And the building blocks of this work has been made through, I would say about 15 years. And also through, I'm very pleased that this work is in collaboration with 3 of my former PhD students. And you see that they passed their thesis about 6 years apart from each one, from one to the other. And we built through this thesis the building block necessary to do this work. And the last one is Mohammad Farhat, who just passed his thesis and is now in a Miller Fellowship in Berkeley. So the question is a question about the Earth and the Moon. And you know that the Moon is always showing the same face to the Earth. And you probably know also that the reason for that is because of the tides. The tides, you know them well because you've been to the beach playing on and you know that there are usually 2 tides a day. And these tides are due to the effect essentially of the moon, but also of the sun. I just put the moon here. So you have the moon attract this part more than the center of the Earth. So you have a bulge here, but you have also a bulge here because it is attracted less than the center of the Earth. This is the first order effect. But if you look more precisely, you will see that the bulge is not exactly in the direction of the moon. Because the Earth is rotating fast and that the deformation is not totally elastic, the rotation shifts a little bit the bulge from the direction of the moon. So there is a torque that tends to slow down the rotation of the Earth, and by conservation of the angular momentum, the moon goes away. The first to understand that was George Darwin, one of the sons of Charles Darwin. And in a very important work in 1879, he totally understands this problem, and he says that since the moon is tending to retard the Earth's diurnal motion, it is obvious that the Earth must exercise a force on the moon, tending to accelerate her linear velocity. The effect of this force is to cause her to recede from the Earth and to decrease her orbital angular velocity. So you see, it is known for quite a long time. But then the question is, how can we observe this effect? And especially in the 1900s, can we observe this effect? In fact, it was possible to observe this effect. And the way to observe it was to analyze the old eclipse. When you analyze the old eclipse, you see some shift from the predicted position to the position where the eclipse occurs. And there is especially this work by Spencer Jones in 1939 who did this work. So you see, there was in particular some eclipse that was predicted to occur in Babylon. So you see, you need to have some very precise recording to do this kind of work. But here, you don't need to have something precise. You just need to know where the eclipse occurs. If you make the computation and predict that without any tidal dissipation, the eclipse occurs here, and you have the record that in 136 before Christ, it was seen that the eclipse occurred in Babylon, you easily know that there was a shift in the rotation of the Earth, an offset, which you can precisely measure. And in fact, if you take the present, when you put this offset, this is what we do in the modern computation. For example, if I take the ephemeris from IMCCE, if I look, I have actually that the eclipse go in Babylon. So that was a way to measure precisely this recession of the moon and the slowdown of the Earth. So you can put that data in the equation that Darwin derived, and you make the computation backward in time. And what you find is that if you integrate backward in time, the Earth-Moon distance decreases, and you have the moon that hit the Earth about 1.4 billion years ago. This is what gives you the computation. In fact, this was not a problem. This was not a problem before the Apollo mission. In fact, this computation, the conclusion of this computation was that the age of the moon is 1.4 billion years. And this is, in fact, all the estimate of the age of the moon before the Apollo mission were derived from some similar tidal computation showing when the moon was close to the Earth. And in particular, these about you see, 1950, 1960. But the problem occurs when with the Apollo mission, because the Apollo mission did several things. One thing that they did is to bring back some sample rock. And from the sample rock analysis, geochemical analysis, it was found that the Earth of the Moon, the age of the Moon is not 1.5 billion years, but 4.4 billion years. And you see, from this time, all the analysis gave the same age. So there is no doubt that the age of the Moon is 4.4 billion years and not 1.5. This is one thing. The other thing was the laser reflector that was put on the Moon by the astronaut. And there are several of them. And with this laser reflector, we can measure very precisely the Earth-Moon distance. This is done in particular in grass. And we have this measure at the centimetric level. So we have been measuring the Earth-Moon distance for 50 years at about 1 centimeter precision. So we can deduce a very precise measure of the tidal recession of the Moon, which is 3.8 centimeters per year. So you see, after the Apollo mission, you can still integrate back the problem, but you have now a big problem. You have a big problem, which is that the model gives a time for the age of the Moon that is 3 times smaller than the real age. And since then, this problem stays, and I found it's an important problem. So this is why we are trying to solve. Of course, you can think what could be some observation on the Earth of the past age, of the past rotation speed of the Earth, of the day length, of the length of the day, for example, on the Earth. There's been a lot of various geological measures related to corals, to growth of shell and all this. They globally show a decrease of the length of the day when you go back in time. So the Earth was rotating faster, but nothing growth of coral. They try to relate it to the tides and things like that. I will detail some more later on, but these I don't want to debate too much on this because you see, you have that's the problem. There are a lot of geological data, but they were not very trustworthy in some sense. Of course, people look to this data and try to say, okay, I will take the model of Darwin and try to change a little bit the parameter to try to fit the data. But you see, depending on the data you take, you end up to solutions that never give the right answer. So the next thing, a big step, was in the 1980. And there was a model made by Webb, who looked to a simplified Earth with just half an ocean, half a continent. And with this, he could solve a simplified model of Navier-Stokes equation, a linearized, in fact, Laplace equation of tides with a Fourier series. And then what he showed is that the tidal dissipation has some resonance depending on the rotation speed of the Earth. And at present, we are close to a resonance. So in this case, it gives an idea of a way to go for a solution because we can think that we are now in a relatively high dissipation state. But when you were going back in time, the rotation speed was faster and the speed was slower. But in the model of Webb, none of his model gave a proper solution. Sometime 4 billion years, sometime more than 5 billion years. So this problem was away for a long time. And it's funny because just as I proposed this work to Mohammad Farhat, In fact, at the same time, there were several papers published on the subject with a sophisticated method. Some in the same way of Webb, but with more sophisticated method. And what people try to do, they try to make the model fit the data. You see, try to make a model that fits the data, but we are totally off with the age of the moon. In the same way, there were some more numerical work, also very recent, like this one. They also try to fit the data. So the numerical computation is very cumbersome. They also try to fit the data, the beginning of the data, and it's totally off. These are numerical estimate, but not related to the simulation. So you see, we are totally off. We are here at 45 Earth radius and are still at 4.5 billion years. So this was the status when we start this work. And what we did, I've been working for 30 years with geologists, so I know well the geological data. So our first assumption was to make we wanted to make a new semi-analytical model in the line of Webb. And the first idea, an important idea, was not to take into account the geological data. Because I know them, yes. Because, yeah, the idea was to say, okay, we will first see what we can do without the geological data. It doesn't mean that I will forget about them, and I estimate well my colleague geologist. But we want to make a physical model as simple as possible, but not too simple. You may know this sentence. And with a minimal number of parameters. And in this case, it will be 2 parameters. And why 2 parameters? Because it occurs naturally. And the good thing is that we also know very well 2 quantities. These 2 quantities, which I tell you, are the age of the moon and the present Earth-Moon tidal dissipation. So we will first try to see if, with a model with 2 parameters, with 2 well-known quantities, we can do something. It's not obvious, but we'll see. Mohammad took also into account, because he wanted to complexify things a little bit, he took also into account what we know of the plate tectonic evolution, but we are still with hemispheric Earth, with half ocean, half continent. So it is an average evolution of the Earth over the past billion years, where we know the data. The idea also is that at the beginning, the Earth was a global ocean. Everybody agrees on that. Everybody agrees on what is the continent now. But you see, people don't much agree on what is the path from going to here to here. We don't care. We will just say we will go from a global ocean to an hemispheric ocean at some time. So the global ocean, you have 2 parameters. One will be the depth of the ocean, and another one will be a friction parameter at the bottom of the ocean. So you have these 2 parameters that are also, in the case of the hemispheric ocean, you have also the rheology, you have the deformation of the ocean, you have the response of the inner Earth, but also there are no additional parameters there. You have this 2 parameter problem, and you integrate, and you find similar result. You integrate basically this Laplace equation, so the fluid equation for the ocean, and you have this resonance that occur depending on the rotation speed of the Earth. And we are now about 1 here, so you find, as in Webb, that we are close to a resonance, a main resonance here. And depending, if you have a global ocean, you have some very isolated peak. If you introduce the hemispheric continent, you have a spectrum that is much more complicated because of you break the symmetries and you have lots of additional peak. This is depending on the dissipation factor in the bottom of the ocean. So you have this model. So what we'll do now is to search for a best fit of these two parameters. And we will do that by exploring all the value of the parameter in a very straightforward manner. So you take all value of the depth of the ocean, all value of the dissipation parameter, and for each of these dots, you integrate the model and you look if it fits with the two well-known quantities that are the age of the moon and the present tidal dissipation. The blue point is where the fit is good. So you see like that, you have one well-isolated place here, which corresponds to a depth that is 4.6 kilometers. And it occurs that if you take this value, it gives you a volume of the ocean, which is very close to the actual volume of the ocean. Same thing for the dissipation parameter. It is a very plausible parameter. And you see the fit. You have an excellent fit, 3.829 instead of 3.83 for the recession of the Earth, and 4.43 instead of 4.425 for the age of the moon. That was not expected. We didn't think, starting from this simple model, that a set of parameters it could well happen that we would be always very far from the solution. No. Here you see that you have, from basically the first try, we get a set of parameters that was perfect. So we thought, okay, this is too good. This is the root mean square. We will look also to the more simple model. Let us look to a global ocean. If you take a global ocean, you always also find a very good set of parameters. It is not as good as here, but if we had only this, we would be very happy. You see the 3.833 is 4.42. It's very good. And if we take the model of Webb, the initial model of Webb with the hemispheric average ocean, we have also a very good fit. So, okay, so now we have to, maybe we did too much work, in fact. Maybe the global ocean, the most simple model, was far sufficient to do the work. So what we did now is I remember that I have some good friend geologists. So now we will look to the geologist. And we will look to all the data that are available, and specifically the best of them. So I will look to two kinds of data. One is some tidal deposit that occurs in a delta, and they are related to the tide. You see, when the tides go down, you have some current, and you have only coarse material that will deposit. And when you have the tide is still, you have the small material that deposit. So this makes these layers that are related to the tides. Like that, you can deduce the day period and the month period, the lunar months, and eventually related that to the year, and eventually get everything. This has been done. I must say that these data are sometimes very controversial in some sense, like any data that is related to lamina, deposit lamina, because you have, you see, for example, here, this was analyzed, the same data in Australia was analyzed by two teams, and they give different results. Here it was analyzed by the same team, and depending the way they make the analysis, they get different results. This is in time in billion years. This is the Earth-Moon distance. We are at present at about 60 Earth-Moon Earth radius, the Earth moon distance in Earth radius. So this is the first set of data, which I must say is not the most reliable. But recently, there is another way that has been designed to be able to find the past state of the Earth. And this is by looking to paleoclimate record. So I recall you that the Earth, here you have Mercury, Venus, the Earth, and Mars. All these orbits are moving because of the perturbation of each other. Here we have 400,000 years elapsed. The orbits are moving. So all this induce some change of insolation on the surface of the Earth. Also, you have the precession of the Earth. So this will change the date of summer, whether it happens at perihelion or at aphelia. So it changes the contrast of season. All this will change the insolation of the surface of the Earth. And this is the main driving term for the climate, for the past climate on Earth. This is what is called Milankovitch theory of climate. And you basically have precession period 20,000 years, obliquity 40,000 years, and eccentricity 140,000 years, and 400,000 years. Here you see the insolation. The fast period is the precession, and the slow envelope here is the eccentricity. So the idea is to recover this period in the sediment, and for this you rely on deep sea core that are made. Why deep sea? Because the advantage is that the deposit is very slow on the bottom of deep sea, like 3 kilometers deep. The inconvenience is that you need to put 3 kilometers of pipes and then another kilometer to make the digging. So it is a very complicated work. The boat has to stand still, even in very rough ocean. You see, I know some, we had some meeting with, we had some direct connection to Zoom connection on the boat, which was just south of Africa. You see, in a region of 40, what is the 40, les 40e rugissants? What? Roaring 40s, yes. So roaring 40s, yes. So it was not very comfortable for the people on board. But you get this very long record, and you see the sediment change, and this change is due to the change of climate. And when you get these and you stack them together, you see you can compare them directly to the extent to the insolation. So this is the motion of the planets and the spin of the Earth's precession, and you see you have this very good comparison of the two. There is a very close correlation between the two. So from this record, or similar record, you can derive what was the past precession period of the Earth. And from the precession period, you deduce the Earth-Moon distance and the length of the day. So you have this record, and we, so several, what we are interested in is very old record. So there was this paper made, you see, it's relatively recent. It was in 2018, and this one by our colleague in Netherlands at 2.4 billion years here. So we think that these blue dots here, they come from cyclostratigraphy, so these analyses. And so this is this is this one. And we think really that this is the most reliable method to obtain the past state of the Earth. It's difficult. It's not all record that can give it, but it seems to be reliable. When different teams analyze the same data, they come to the same conclusion, which is already a good sign. So now we will compare these three different models, starting from the most simple one to this data. The global ocean, you see that, of course, they start from the same place and they end to the same place because these constraints are well satisfied. And now the hemispheric average ocean, which is not as good if you want to reach these data. And then our model, our combined model, which is like that. And I must say that we were extremely surprised to such a good fit. Especially this point here, you see this point was made just as we were doing this curve. Our colleague from, they had not published it yet, they sent us their data. And when we put the data, it was right on the curve we made. Both teams were very pleased because, because you see, it gives a lot of credit of the method that is used. And I must say that, yeah, we were extremely pleased with this model. And you see, this is the evolution of the tidal torque. The tidal torque as present is here. And then you have this resonance here. So at the time you have resonance and this big resonance here, at the time you have resonance, you have an increase of the tidal dissipation. So you have a change, big change of the steep change of the Earth-Moon distance. So instead of having some kind of monotonic, or it's always monotonic, but a steady changing variation of the Earth-Moon distance, you have some steps like that. We don't. We switch at some point, or we switch from the global ocean to the hemispheric ocean at a point. We just decide that the switch will be at a point where the two torques are the same. So to keep continuity in the model. So there is not an introduced parameter. Of course, it is artificial, but it's relatively at a good distance, and it is a model with some continuity, which is what we want. Of course, this is the Earth-Moon distance, but you get as well the length of the day, so that the evolution of the length of the day in the past. The curve is the same. You go from one to the other one, so you will have the same fit with the data, because basically the data are transformed with the same transformation as the curve. But it gives you, you see, for example, 1 billion years ago, the length of the day was 19.5 hours. So I would not like to live 1 billion years ago, because I found that already length of the day is too short. So that's, yes, that's, but we may end up with other problem in a billion years. So and this is what this is some new data that has been, you see, this was published in the end of 22. And it was published in IA. In fact, Mohammed got the IA thesis prize for this work for 2004. He got also the IAU thesis prize for the same year. And since that time, this motivates a lot our colleague geologists, because they had suddenly a curve that looks reasonable, that gives some credit to the work they were doing. In some sense, they give some coherence. So there's been a lot of work since then in a very short time, trying to reanalyze some data to do. Also, there was this method, this new method that was set up for this analysis. And since then, you see, we had rapidly these new data points here and this one. So the red one and the orange one, published in 2003. And we had very recently, a Chinese colleague, geologist, came for 1 year in our lab. So you see, we are having a geologist in our lab at not very normal, usual for Institute of Celestial Mechanics, but pure geologists. So the people who dig, who break the stone, you see, not theorists. And we have all these new data points that was published in August this year. And And this was, of course, there is still a lot of uncertainty, but it seems to confirm the existence of this tear. We don't expect that the exact position of the resonance will be that. They may change when you go to a more complicated model. But the idea is that the global behavior is robust, and the global analysis is robust. And now there is a very interesting interplay with the data and with the geologists trying to check. So this is one of the papers. There have been 3 papers with a lot of data that have been published this year or will be published. I have one which is not yet published, but it will be probably in Science Advance. And so you see, when you see that, you think that, oh, that's done. We have the good scenario now. There will be only minor change, improving the model, going to a more realistic continental distribution, because you see hemispheric continent, maybe it's not that realistic. So this is the kind of thing we are experimenting now. But in fact, there was some issue that came out just last year, and that was about the possibility that in the past, the rotation speed of the Earth was locked during about 1 billion years or more. And it was locked, it doesn't stop, but the variation, the length of the day was locked. So and this came from an idea that was emitted by Kevin Zanley together with James Walker, and that was in 1987. And we had Kevin make an AstroGeo seminar, if you are interested. It's a very interesting, I think that I will discuss of the problem, but I just give you the QR code of this video. It's a very interesting piece of working science and history of science, I think, because so this hypothesis is whether it is possible to block the rotation of the Earth by another effect, which is atmospheric thermal tides. So what is the problem? You have, as I said, the body tide and oceanic tide that slow down the Earth. But you have another effect, which is the atmospheric thermal tide. What is atmospheric thermal tide? The sun is heating the atmosphere, and because of that, you have a redistribution of the mass of the atmosphere. The particle goes away from the heating point, and you have a bulge, a diurnal bulge, but also a semi-diurnal bulge here. And this one is orthogonal to the direction of the sun. But as the Earth moves rapidly, the bulge is shifted. But now you see it is an accelerating torque, depending on, of course, of the shift. But if the shift is moderate, you have an accelerating torque. So right now, this effect is about 6% of the total tidal dissipation. So it doesn't really count. You have the recession, the dissipation. But the idea is that in the past, the oceanic and body tide was smaller. This is what I show. And there is a resonance for the atmospheric thermal tides, which is called the Lamb resonance. So for a faster, at a given position, at a given speed rotation, there is a possibility of a resonance with an increase of the atmospheric thermal tide. So the idea was that maybe at some point, there were 2 of the same value. So the rotation speed was blocked. And when it was blocked, it stayed in this value, it stayed in the resonance. So it can stay for a long time. And this was the idea of Kevin Zanley. And so that the Earth was stopped in its rotation for about 1 billion years and even more here. And these were this was reanalyzed relatively recently. You see, it's funny. You see, for 30 years, nobody made a paper on that. And then in 16, there was this paper by Bartlett and Stevenson from Caltech, and which did this analysis. He reanalyzed this resonance. And So the question, and you see it's a big effect. So the problem, did that occur or not? It's not a small thing. But it was 1 billion years ago. So it's difficult to find the record of what occurred 1 billion years ago. And as we just published our paper, which show basically that everything was solved in the Earth-Moon descent, because this scenario were made also because at the time nobody could find a good scenario for the Earth-Moon evolution. So it was trying to fit some data that were here. So there was a place for lots of possibility. So just as we have published our paper showing that we have solved everything, there was 2 papers published in Nature Geoscience and Science Advance that showed that there was this tidal locking in the mid-Proterozoic. And that, so one paper was a geologic team. What they did was to take all the data that they could find, and they look to the slope, and they say, oh, look, here you have a good slope like that, and here you have a plateau, and here another slope. So you had a locking of the Earth-Moon, of the length of the day for 1 billion years. Nature Geoscience. And the problem is there were these 2 papers that were published about 3 weeks apart. I will speak of the other one. One is geology, one is geophysics. The other one in Nature Geoscience, and the other one in Science Advance. And they both advocate for this locking of the day. So at the same time, we were aware of this atmospheric tides, because we had worked a long time ago. In fact, the thesis of Pierre was on thermal atmospheric tides. So this is a problem we are very well aware. And by the time with Mohammad, we had done a full analysis of the thermal atmospheric tides and trying to see if it was possible. Basically, I will show you, our result was that it was not possible. But when we submit this paper in some journal, the reviewers say, oh, but you are thoroughly wrong because there are 2 papers that are published in Science Advance and Nature Geoscience that say the contrary. So we had to discuss precisely on this paper. And this is what I will say here. So you see this data, okay? They have, you see this fit. Oh. You can think of what you want of the method, but let us look to exactly what our model gives. Our model gives that. This is the curve I just showed you. So you see, it goes very well to all the data, except here. So what are these data? That's the problem. What are these data? These are stromatolite data. So it is the growth of stromatolites 2 billion years ago. And mainly from one single author, which is Panella in 72. What does Panella say of his data? Panella says the major drawback of stromatolite is the incompleteness of their sequence. And he says that we cannot take them seriously. We can just, because the problem, you have layers that accumulate, but sometimes they are dispelled. So the only thing you can say is that maybe you have a bound, but certainly not an exact value. And when Bartlett and Stevenson reanalyze that, they say also these data, particularly the early stromatolite data by Panella, should not be taken too seriously. But this paper in fancy journal, take it seriously. And the other paper is this one. You see, it was funny because this is July, I don't know. It is July 7. And in this paper, this is a very obfuscated paper. When you read first the paper, you have the impression that they have used a big JCM to make the analysis. But in fact, they don't really take a big JCM to make their analysis. What they do it at the end. but in the real core of the work, what they do is they have a kind of empirical model derived from web model with 16 parameters and with quantities that are multiplied by 40 in order to what they want to do is try to fit changing the parameter as much as they can, splitting things in several pieces, adding 16 parameters to try to fit the data that they think are the good data. And they get a model with this locking of the length of the day. But you see, what do they try to fit? They try to fit this. And what is this? This is, again, Panella data. And I plot here what is our solution. This is our solution. And you see, in particular, these are the data that we think are the most reliable, which was not known by this geophysicist. And they don't go here. So again, this is related to this data, and which we think are totally nonsense. In fact, on the plot, they are also not plotted at the right place, but maybe they did the work because it's complicated to read all this geological literature. It's not so easy. So that's the advantage of working closely with geologists. You know really the literature, you know the data, you know what they are, you know what you can rely on, what is not very trustfully. And if you speak to that of geologists, they will say it's nonsense. It's well known that these Panella stromatolite data are not reliable. So, but some geologists still think they are, but okay. And what was, in fact, the work made by Mohammad, it was to reanalyze completely with a big model the effect of the thermal tides and look there are two parameters in this model. One is some absorption efficiency, one is some radiative transfer frequency. You have these two parameters. You can put what would be the value, the threshold of the amplitude to get the crossing of the resonance either in the Precambrian or in the Mesozoic. And you find that the value for the amplitude at the equator of the tidal, of the atmospheric thermal tide is 480 Pascal. And if it is at this time, it is 1500 Pascal. Right now, you can see the thermal tide. I have done, in fact, all this work, I didn't tell you, but all this work started from an experiment I did in my garden a long time ago. What I did is I had a quite nice atmospheric station, meteorological station, recording temperature, pressure, and that. And for a full year, I recorded minute by minute the barometric pressure. If you do that, you have something that changed a lot from about 950 to 1050. That's a big change, meteorological change. But if you fold everything over one single solar day, basically everything that comes from meteo will cancel because it is chaotic and it will average to zero, and only remain the forcing term. And this forcing term, you see a very clean signal with two maximum at 10 o'clock and 22 o'clock, which are in fact the bulge that I showed you before. And when I saw this curve, I thought that, because I had worked with Alexandre Correa for Venus, for understanding the rotation of Venus a long time ago, but we didn't at the time fully understand this problem. But when I saw this curve, which was so clean that it comes out in a very, basically the uncertainty was in the thickness of the curve. I thought that we really need to understand totally this problem. It is so clean that we need to understand it. And the work of thesis of Pierre Auclair Desretours was to understand this curve. During his first year and a half the time of his thesis, he had this curve, temperature curve and pressure curve, and he tried to make a model that will fit this curve. And from that came a general model, and then the general model for atmosphere also could transfer to ocean. And then we did this work, among others, on the Earth moon. So this derived from that. You see, you need this value for the pressure, and the present value is 100. And what is interesting is that just this year, very recently, another analysis was made. Another analysis was made about these thermal atmospheric tides and published in Nature Geoscience in July. And in this paper, the main goal of the author was to try to say that there may be some increase of temperature at the time of the resonance because of the increase of the atmosphere. But at the same time, they did some very refined computation about this, this time with the GCM, about this Lamb resonance. And when you see their curve, this is their curve. This is the present value of the amplitude of the thermal tide. You see, 100 Pascal, as I was saying. This is what you can see. In my garden, you find only 40 because it depends on the latitude. But at the equator, it's 100. So this value, this point, you can do it experimentally in your garden. That's it. And you have this resonance. You see, you have an increase and a decrease also. So when you increase here, you have an accelerating torque. But you see the value, it is only 130, 140. What they conclude in their paper is that according to estimate of the lunar torque during the Proterozoic and the present day solar torque, an amplification of 7 in the imaginary component of the pressure anomaly is needed to achieve the balance. So this 7 is in between these two values. Our simulation yields a factor of only 1.5 increase on the accelerating side. Here, 1.5, where you need 7 to get the equilibrium. So what should be the conclusion? If you see that, the conclusion should be that the amplitude of the Lamb resonance is not large enough. What was the conclusion of their paper? After saying that you need 7 to make the equilibrium and you have only 1.5. In fact, it was very obfuscated, but what they say is recent modeling suggests that this locking scenario was the most likely of possibility. So here you have a paper that shows precisely with a sophisticated method, with a most up-to-date method, that you need a factor of 7 to get the resonance. You find only 1.5 in your model. And you say that the most likely probability is the locking. You just think you are crazy. You see, that's and that's really, I would say that that's really an example of bad practice in referring process for paper who wants to go to fancy journal. Because obviously a referee didn't wanted to see that the model was destroyed basically by this paper, confirming what we had said. But the main goal of this paper was not that. It was just a side result. So the author were a little bit, they wanted their paper to go through the Nature Geoscience. So they had to change. Their first wording was not this one. They had to change it, obviously. So in fact, we ask the author to change, to make a correctum, an errata, and they did it. They did the errata, you see, and it was published 25 July. And they say this difficulty with resonance locking process were predicted in the theoretical study of Farad. Then here they acknowledge our results are consistent with their prediction in terms of the strength, timing, structure, and asymmetry of the pressure anomaly field near the Lamb resonance. Here they acknowledge. So it's funny, you see, you have obviously some referring pressure that push to say something, and in the errata they say the contrary, which is in fact normal, you see, because the data was showing that it's not possible. And my last slide is again a very recent paper published by some Chinese colleague and American colleague, geologists that make also some analysis of data points, looking to there are new points here. And what their conclusion is also that in the geological, using this, I would say, most reliable geological data, they don't observe any evidence of the locking of the day, and say our results are fully consistent with the Farad 22 model. And that will be my last slide.
Thank you very much. Yes, Henri?
Yeah, so thank you for that very interesting talk, especially we don't normally hear about all this kind of great geological stuff. And also I have even less respect now for nature than I did at the start of the talk. Can you just comment on what is the mass of the atmosphere compared to the mass of the oceans? Because I have a hard time believing that the atmosphere could really have so much an effect on the rotation of the Earth. Is that important or not?
Oh, it's very small, but I don't remember the figure. I'm sorry.
But because it's very small, then does that mean that it should be less important in changing the length of the day?
It's like you know, when you compare the mass of the ocean to the mass of the Earth, the mass of the ocean is a very little part of the Earth. I don't have I should put this. I should have a cheating note to it. Yeah, I should put this because I have that's a very natural question. But I can tell you it's very small. It is, you see, you can think of it when I say it's about 2 kilometers average depth. If you were putting the water all over the surface of the Earth, 2 kilometers compared to 6,000. So this gives you an idea of the importance of the ocean. So, and despite that, 9/10 of the dissipation come from the ocean. So just to show, but I don't have in mind the ratio with the atmosphere. But it is a small. So the ocean is a small part of the Earth, and the atmosphere is a small part of the ocean.
Yes, thank you very much. It was a wonderful talk, and also I appreciated the last part on, keeping your head when you publish papers. So I have a curiosity about what happens at the bank.
What happened?
At the bank, when you integrate backwards, the orbit of the moon, at some point you had the bank. So what happens there? And, when the distance between Earth and moon is very small, do you have to take more of the deformations into account? So I just have problems.
You want to know what happened?
Yeah, exactly. Both physically.
Okay. So the first thing I should say is that we don't address what happened here. Because, of course, when you are at the very beginning, this is, you see, what is here, it is, the evolution is extremely fast. Because the tidal dissipation is the square of a tidal effect. So it goes as the inverse of the distance to a power 6. So when you go close to the Earth, the evolution is extremely rapid. And so here, of course, we don't address this problem, but also because all the physics will change here. Because you will have magmatic Earth, you will have magmatic moon, and so you will have a first evolution after the impact, you know, the moon formation is supposed to be that the most acknowledged model. It's the result of a big impact of a body like Mars that hits the Earth, but the two bodies are then magmatic. And you have this very quick evolution at the beginning and the reaccretion of the moon. And then there will be a fast evolution, but this evolution needs to be made in a context of magmatic planets where the dissipation will be different. In fact, we just submit a paper on that. And this is different. And here we reconnect from after these are solidified. So you get the present physics and you go to the present state.
Hello, thank you very much for the talk. In the last slide that you showed, in the work by some Chinese and Americans, there is a yes, it seems to me that there is a data gap between somehow between 500 and 1,500 gigayear. And I don't know, and this can completely change the fit. Therefore, I don't know if anybody is trying to find data to this in this region.
You can imagine that since the publication of this work, of the work in 2002 to 2022, there's been a big, and also because of this controversy about these thermal tides, and I clearly show, in fact, I published a paper in a sedimentology journal, really showing what I am presenting to you, showing this controversy and telling geologists that we need to have new data in this interval.
Okay.
And this is part of this, because you see, they have been putting this point here, for example.
Yes.
But each point, you can imagine, it's a huge work.
Yes.
It's a huge work. So data are not, good data are not that frequent. You see, it's not, so it could be a lot of work. If it is a core, if it needs to core, a coring, it's like a space mission. You need less expensive, but a small mission. So you need to find a fund. It's 200 million euros, something like that. So you need to. So, but there is a big motivation to try to fill this gap now. People are very excited about that.
Thank you.
And as I say, there was, so that was published in Science Advance. There was the other paper published in PNSR and PNAS, and there will be another paper that will be published. I don't remember if it is in Science, also with, also with similar data. So there is it has motivated, you see, nothing for a decade, and then suddenly everybody, because both, there has been the development of this method for deriving in a more reliable way this data, and our work that showed the interest of doing it. So suddenly everybody is very eager to work on that and trying to get to really, so you see, to really the evolution of the Earth-Moon distance, and as I tell them, we don't say that our curve is the Bible. So now we need an interplay with geologists to show what would be the real model.
Okay, last one, Luc.
Would it be possible that you add to your model some module computed numerically to describe very accurately, say, the last 500 million years in order to describe very accurately the evolution of the continent, plate tectonic, internal structure of the Earth and Moon, and so on? So that you check that your model, it does not change very much your model.
Baptiste Loire just started his PhD thesis exactly on this problem. And as we don't want to, we work here, team with, I like to work with where the knowledge is. So we team with people from Laboratoire Jacques in Sorbonne University, who are the best people for understanding numerically PDE. And in particularly, we do it with the FreeFem++ software. And we have in this committee, we have the builder of FreeFem++, Frédéric Echt, and also Yvon Madet, who has been leading this team. So, and this work is advancing really well. So we are now looking, so this shows you the kind of distribution of continent we are looking for. So we want really to look to how stable is the model, what would be the impact of, it is not easy, but so you see, it's the same thing. I don't care about the tool I'm using. I want to solve a problem. So we will use any tool that is suitable for solving this problem, even doing some huge numerical simulation with, and to really answer your question, what is it? Also, we want then to propagate it over what we know from the continent evolution. So we will not try to make a very precise model, but we want to have a robust model that we could propagate with the continent evolution of what we know of it over the past billion years.
Okay. So thank you very much. Let's thank the speaker again.